classification of the singularities. Yeah. So, today we will continue with this same concept, the singularities, and also give various type of singularity, concept for the various type of singularity, and then go for the residue theorem that will be used to evaluate the sum of the real integrals, which may be in the form of minus infinity to infinity f x dx and so on and so forth. So, today we will try to cover up this thing, because this may be the last lecture today for this. So, as we have discussed, the singularity we have defined as we call a point z naught or a function f z is a singular a function f z has singularity at a point z naught if f of z f z, if f of f z is not analytic at z naught, that is cease to be analytic, but every neighborhood of z naught, contains points at which f is analytic. That is, the meaning is, if suppose we say z naught is a singular point for a function f z, it means at the point z naught the function cease to be analytic, either it is not defined or is not at all analytic. And but if we draw any neighborhood around the point z naught, then this must include some of the point or maybe all also, where the function should be analytic. If there exists a neighborhood of the z naught which is free from any other singular point except z naught itself, then such a point z naught is called an isolated singular point. So, we call the point z naught as an isolated singular point of f z if z equal to z naught has a neighborhood without further singularities of f z. It means there exists some neighborhood, there exists a neighborhood of a point z naught with a suitable radius delta naught, such that this neighborhood is free from the singular point of f z except h z, means function is analytic everywhere in this neighborhood except at z naught. So, at all other point f is analytic. F is analytic at all points z belonging to n delta z naught except at z naught, which is a singular point, except z naught, which is a singular point of f z. Then z naught is called an isolated singular point. An example we have seen, that if we take the function f z, which is tan of z, then obviously this function has a singularity where cosine of z is 0. It means z must be odd multiple of pi by 2, like this. So, these are the singular points of this, and each one is an isolated singular point, because there is a sufficient gap between pi by 2 and minus pi by 2, pi by 2, 3 pi by 2. So, one can obtain the neighborhood with a suitable radius which does not include the other singularity except the point itself. However, if we look the function f z, which is tan of 1 by z, then it has a singular point. The singularities of this will be all the singularities will be where the cos of 1 by z is 0. It means 1 by z must be the odd multiple of pi by 2, all these, that is 2 n plus 1 odd multiple of pi by 2, is it not. So, that is all n is 1, n is 0, n is 1, n is 2, n is 3 and so on. Now, z becomes what? Z is 2 over 2 n plus 1 pi. So, these are the singular points, these are the singular points of this. Now, once you take the limit of this. So, what is the limiting position of this? Limit of this as n tends to infinity, this limit is 0. Now, if we look the 0, this is our 0, here these are the sequence of the points, these are the sequence of the points which are tending to 0. So, if we draw any neighborhood around the point 0, then you will get at least one of the point, at least some point of the type of these 2 over 2 n plus 1 pi will be available, is it not, like this. So, will be available for this. It means 0 is not an isolated singular point. So, here 0 is a non isolated singular point for the function f z, which is tan of 1 by z. So, this is the difference. We are interested in a isolated singular point, and if the function has an isolated singular point, then we can classify by means of the Lorentz series. Okay. So, classification of the singular points. Singular points. Let us suppose, let z equal to z naught be an isolated singular point of the function f z. So, we can expand it. So, we can expand this function f z in the form of Lorentz series in the neighborhood in the annulus 0 less than mod z minus z naught is less than say r, where r is the radius of this annulus, means outer circle, where the singularity, all the singularity other than this z naught will lie outside it. So, this is our z naught point, and here if I just remove it with a small portion say delta, this is our delta, this radius, then we get this annulus 0 less than mod z minus z naught less than r. In this annulus the function f is analytic. So, it can be expressed in the form of the Lorentz series as follows. So, we get the f of z as 0 to infinity a n z minus z naught to the power n sigma n is 1 to infinity b n over z minus z naught to the power n, where a n's and b n, if you remember, this can be defined by means of the formula h. A n's are 1 upon 2 pi I integral c f z star over z star minus z naught to the power n plus 1 d z star, and b n's are defined to be like b n's, we can write it minus n plus 1 b n's we can write 1 upon 2 pi I integral over C f z star over z star minus z naught minus n plus 1 d z star. That is a single formula, we can write it in this fashion. And so, B 1 is nothing but what? When n is 1, it is nothing but f z star over z star minus 1 n is 1. Okay. So, B 1 will be integral of f z d z. So, this is what we get. Okay. Now, if we look this series 1, then it consists of two parts. One is the integral, positive integral powers of z minus z naught, other is the negative integral power of z minus z naught. The first one will be represents an analytic function, it is a power series. The second one, it is known as the principal part of the function f z of this series. Okay. Now, the singularity z equal to z naught is a singular point. So, the characterization or classification of the singularity depends on the terms available in the second part. If there are finite number of terms available in the second part, then we say z naught has a pole and the order of the pole is the number of the terms available in the second part. If there are infinite number of the terms available in the second part of this expansion, then z naught will be an essential singular point. So, we say we define like this, if the principal part that is second portion, second part of it in one contains only finitely many terms, say V 1 over z minus z naught plus B 2 over z minus z naught whole square, n is 1, n is 2, and say B m over z minus z naught to the power m. Then the function f z has the singularity, has the function f z which has a, then the function is said to have a pole of order m at the point z equal to z naught. Means this single point will be a pole of order m if the negative powers of z minus z naught in that series having only m terms, then it is of order m. Now, on the other hand, if the principal part of one part of the series 1, that is the second part of series 1 contains infinitely many terms, then we say the function f z has at z equal to z naught an essential singularity and an isolated essential singularity. Essential singularity. Okay. For example, if we just look the function f z which is e to the power 1 by z. Now, this function has an expansion which is 0 to infinity 1 by factorial n into 1 by z to the power n, that is it has an expansion as 1 plus 1 by z plus 1 by factorial to z square and so on like this 1 by. So, it does not have a positive powers, only one term is there, constant terms, and rest are zeros. So, the negative parts contains infinitely many terms. So, z equal to 0 is an essential singular point for this. Similarly, when we get sin 1 by z, we get the similar term. If we take the function f z, say 1 by z cube minus z 5, say, then in that case it is equal to what? 1 by z cube, then 1 minus z square, is it not? And then when we expand it in the form of the series 1 by z cube, 1 minus z square inverse, we get 1 by z cube, 1 plus z square plus z 4 and so on in the circle mod z when less than 1. And in that case, we are getting 1 by z cube plus 1 by z plus z and so on. So, basically these are only two terms, z equal to 0 will be a pole, but there are three terms because z square term is missing. So, z equal to 0 is a pole because it is the first term. If you remember b 1 by z minus z naught. So, that is available 1 by b 2 is missing, b 2 is 0, b 3 is z cube. So, is a pole of order 3, 4 of order 3 like this. Similarly, one can get. Now, if we see here the difference between the essential singularity and the pole is that if z naught is an isolated singularity, you write down the expansion of the function in the form of Laurent series, and that the negative part of it, that is the principal part of it, will decide about the nature of the singularity, whether it is a pole or it is an essential singularity. But someone may think like this, because in pole also the terms are though it is finite, but the z minus z naught lies in the denominator. So, when z approaches to z naught, it goes to infinity. Same case is with here also, z, all the terms are lying in the denominator. So, one can think that both are tending to infinity when z is tending to z naught. The answer is not satisfactory. Why? The behavior of the function in the neighborhood of the pole and in the neighborhood of the essential singularity is different. In fact, in case of the pole, the modulus of f z will always go to infinity when z approaches to the singular pole z naught. But in case of the essential singularity, when z approaches to z naught, the value of the function f z, f of z may not definitely will not approach to a single limit, it will approach to different limit. And in fact, if I take any number, any given complex number, one can identify a path which approaches to z naught such that limiting value of this function f z when z approaches to z naught an essential singular point, it will lead to the same value which we desired, except possibly 1. So, the characterization of this singular point about in the neighborhood of the pole and neighborhood of the singularity differs, and that is given by in terms of the following result. The first, the characterization of singularity behavior, or you can say behavior of the, do not say behavior of an analytic function, behavior of analytic function in the neighborhood of pole and essential singularity. Essential singularity. So, first we have behavior near a pole, behavior near a pole. ठीक behavior near a pole. It is given like this: if the function f z is analytic, and has a pole, at z equal to z naught, then the absolute value of this modulus of f z will tends to infinity as z tends to z naught, in any manner. It means, whatever the path you choose which approach to z naught, the absolute value of mod f z, the modulus of f z will go to infinity. That is the if z naught is a pole. For example, if we look the function f z, which is 1 by z square, now it has a pole of order 2 at the point z equal to 0. Now, when you find the limit of this mod f z, when z tends to 0, this is the 1 by modulus of z square limit z tends to 0, and that is nothing but what? X square plus y square limit x tends to 0. And this we can establish by epsilon delta definition also, or otherwise along any path you choose, this limit will go to 0. This will go to infinity, because z is x is tending to 0, by tending to 0. So, this will go to infinity, whatever the path you choose, because it keeps on increasing for that. Okay. So, this goes to z tends to. Similarly, the behavior near an essential singular point. Near essential singular point. Essential singular point. The function f z, this behavior is given by Picot's theorem. What is the Picot's theorem is? The Picot's theorem says, if the function f z is analytic and has an isolated essential singular point, isolated singular point at a isolated singularity, singular point say z equal to z naught, means it has isolated singularity at z equal to z naught, then it takes on every value, with at most one exceptional value in an arbitrary small neighborhood of z naught. Arbitrarily small neighborhood of z naught. So, what this theorem says is, Picot's theorem says, if suppose z naught is an essential singularity for this function f z, then if I draw a neighborhood around this point, okay, in an arbitrary small neighborhood of this point, the value of the function f z when z approaches to z naught will take any value, all the value in fact, except possibly 1. So, there will be one exceptional value which may not be taken by the function when z approaches to z naught, but rest of the values can easily be achieved by choosing the suitable path which approach to z naught. For example, if we take the function f z e to the power 1 by z. Now, this function we have already seen that z equal to 0 is an essential singular point. the limit of this function f z when z tends to 0. Now, if I take z to be I y, then what happens to this? This is the limit e to the power I y means minus I square over I y, is it not? And that will be the limit by tends to 0. And once you take this, what happens to this? I e to the power minus I over by limit by tends to 0. So, this will be equal to cosine of 1 by y minus I sine of 1 by y and limit by tends to 0. We know the limit of sine 1 by y or limit of this will not exist. So, it does not exist. However, if we choose the path, this is path 1. If we take the path 2, z is equal to say x, then what is the limit of this function f z? When z tends to 0, it is e to the power 1 by x as x tends to 0. Now, this limit will go to, if x is positive, it will go to infinity, if x is negative, it will go to 0. So, along different path it has a different value. In fact, if I choose a function, suppose I want this value c, which is equal to say c naught e to the power alpha different from 0, then one can identify the path which approach to 0. So, that this way. So, suppose there e to the power 1 by z is suppose this value which is c naught e to the power I alpha. So, if I compare it and find out the x and y, we get from here is r square is 1 by ln c naught square plus alpha square and theta comes out to be tan inverse minus alpha over ln c naught. Now, what is alpha? Alpha is this amplitude. So, alpha can be written as alpha plus minus 2 n pi, it makes no difference. So, all can be reduced to 0. It means along different values which is nearby the zeros, we can assume any value with a suitable path. So, that gives the thing. So, we are not going detail like now. Okay. The zeros of an analytic function, another definition which is required, the zero of analytic function. A zero of an analytic function f z in a domain D is a point z equal to z naught in D such that f of z naught is 0. When the function vanishes at the point, then the point is said to be the 0 of that analytic function. A 0 has an order n if not only f, but also the derivatives f prime z, not only f z, but derivative f prime z, f double prime z up to say f n minus 1 z vanishes at 0 are all 0 at z naught, are zeros at z naught, all 0, but the nth derivative of this function is different from 0. Then we say z naught is a 0 of order n, then z naught is a 0 of order n for the function f z. Clear? So, this is also a concept which we require, right. Now, let us come to our main thing which is useful, the residue integration method. Actually, the purpose of the Cauchy residue integral method is to evaluate the integral f z d z along the path C, along a simple closed path, C lying in the domain D, where the f is defined, lying in domain D. That is all. Okay. D. Now, the integral of this f z d z, the two cases may be there. If the function f is if the function f z is analytic, everywhere on C and inside C, then the value of this integral C f z d z will be 0 by Cauchy integral theorem. Okay. So, for evaluation of such an integral is very easy. Just you have to identify whether the given function is analytic throughout the domain contained inside C, at every point inside C, as well as on the boundary of the C. So, integration along the closed path will be 0. However, if the function f z, has a singularity, at a point z equal to z naught inside C, but is otherwise analytic. It means z equal to z naught is an isolated singularity, that is f has isolated singularity at z equal to z naught in the inside C and on C, inside C. Okay. So, there is no other point except C naught and on C, then one can expand this function f z by means of the Lorentz series. Then one can expand it by means of Lorentz series, and the series will be, that is f z will be sigma n is 0 to infinity a n z minus z naught to the power n plus b 1 over z minus z naught plus b 2 over z minus z naught whole square, and so on and so forth. And this series converges, for all points near to z equal to z naught in the annulus in some domain of the form 0 less than z minus z naught less than say r. Okay. Now, in this case the coefficient a n, b n, etcetera, as I told you earlier, this was given by this formula coefficients. This was our formula for the a n and b n. So, if we look the formula for the b 1, here the v 1 is given by the formula 1 by 2 pi I integral along C f z star or z star, and then z star minus z naught minus 1 plus 1 d z star, that is f b 1 becomes 1 by 2 pi I integral along the closed curve f z d z. This is our integral. So, from here can you say integral of the function f z d z along the curve C is 2 pi I times b 1, 2 pi I times of b 1. It means, if I know that the coefficient of 1 upon z minus z naught, then one can easily evaluate the integral C f z along the path C, where the z naught is a point of singular point, an isolated singular point for the function f z. And this B 1 we call it as B 1 is known as. So, B 1 is a very important role, it plays an important role in evaluating the integral along a closed path which contains the singular point, and so B 1 we call gives a special name, and the B 1 is known as the residue, as the residue of the function f z at z equal to z naught. Okay. So, we define the residue, the coefficients, the residue of the function f z means coefficient of, that is residue of the function f z at an isolated singular point z naught is the coefficient of 1 over z minus z naught in the expansion of Lorentz series. Sorry, set 2, okay, Lorentz series 2. So, that is the one way. Means by using this result we can easily get this. So, let it be say here 3. So, suppose I have say this one, say suppose I wanted to evaluate this integral f z sin z y z to the power 4 d z along the unit circle mod z equal to 1 in a counterclockwise direction. Clockwise. Now, obviously, this function sin z by z 4, this is equal to 1 by z 4, sin z expansion is z minus z cube over factorial 3 plus z 5 by factorial 5 and so on. So, when you divide by this, you are getting is 1 by z cube minus 1 by factorial 3 into 1 by z plus z over factorial 5 and so on so forth. So, this is the expansion of the function sin z by z to the power 4 around the point 0. Obviously, z equal to 0 is an isolated singular point. Is an isolated singular point, and then it is of course a pole of order 3. Then what is our residue coefficients? B 1 here comes out to be minus 1 by factorial 3, that is the residue of the function f z at the point z equal to 0. So, if you are interested in this value, then we can get integral of this function sin z over mod over z to the power 4 d z along a curve mod z equal to 1, which encloses z equal to 0 as an isolated singular point, is nothing but by theorem 2 pi I times into B 1 is minus 1 by root 3 1 by factorial 3 sorry 1 by factorial 3, and that comes out to be say minus pi I by 3. Here obviously, this result is valid when mod z is greater than 0, okay, mod z greater than 0. So, it is an analysis like that. So, this way we can easily answer the questions for computing the integral for this. Now, the residue which we are calling as a coefficient of this, then this is not only way to compute the residue, that is by expanding the function in the form of the Lorentz series, and then try to find the coefficients of the 1 by z minus z naught, and say this is the residue of the function. Since the Lorentz series expansion of any function does not depend can not only be obtained with the help of the formula, we can also use many tricks. In many ways we can expand the function around the point z naught and get the Lorentz series expansion, and this expansion is unique. So, you are free to expand the function around the point z naught and get the Lorentz series expansion by either by using the formula, this coefficients formula a n b n's, or with some other method as we have discussed earlier. The main idea is once you expand you find the b 1, but since the expansion, when you expand the function f z in the form of Laurent series either with the help of the formula or with the help of some other way, it requires time, and to evaluate the integral along the closed path f z does not need the expansion at all of the function f z in the form of Laurent series. What does it need is the coefficient of 1 upon z minus z naught, that is the residue of the function at a singular point z equal to z naught. So, instead of going for the expansion, if I know some formula which directly gives the residue of the function at the point z naught, then it is very easy to compute the residue and then find out the value of the integral. So, let us see the residue certain formula to find the residue, to find residue, okay, to find the residue at an isolated singular point, at a singular point z equal to z naught. Okay. So, I will give it different cases. Case 1, if z naught is a pole, suppose z naught is a pole of order 1. Pole of order 1 means that is a simple pole. Simple pole means only the function value f of z naught is 0, but f prime z naught is not 0. So, if it is a pole of order 1, then the Laurent series expansion will involve only the one term, the negative portion principal part will involve only one term, and rest term will be having the positive integral power of z minus. So, we can write down the expansion f z, which may be, which will be in the form of b 1 z minus z naught plus a naught plus a 1 z minus z naught plus a 2 z minus z naught whole square, and so on and so forth. Here b 1 will be different, here b 1 cannot be 0, because if b 1 is 0, then z naught will not be a simple pole. Okay. So, because it is simple, b 1 will be different from 0. So, now you multiply by function f z by z minus z naught and take the limit at z approaches to z naught. What you get? The other term get cancel tends to 0, in fact, it will be 0 and we get only b 1. So, that is the residue of the function f z at simple pole z naught. So, this is the formula for this. Okay. That is the residue of the function f z at z equal to z naught, which is a simple pole, will be equal to limit of the function z tends to z naught z minus z naught f z. So, this will be the formula. Okay. This. Now, suppose for example, let us take if I take the function f z, say 9 z plus I over say z square plus 1. Now, what are the singular point? Here if I look, the z equal to plus minus I will be the singular point, z equal to 0 will also be singular point. So, z equal to plus minus I 0, these are the singular points. Okay. So, I want the residue of the function f z at the point z equal to say I. So, what is this is, you just multiply by z minus I, the whole thing 9 z plus I divide by z, and z square plus 1 can be written as z minus I z plus I, and take the limit as z tends to I. So, if we compute this value, the value will come out to be minus 5 I. That is the residue of the function at z. Similarly, residue at minus I and 0 can be obtained quickly. Okay. Now, if it is a pole, another method is, another rule or is, since if suppose the function f z is of the form p z by q z, where z naught is a simple pole, then obviously, when z naught is a simple pole, the function q z must have a one of the factor z minus z naught involved. So, q z will have a, so q z will have the expansion as z minus z naught into q prime z naught, because when z approach to z naught, q z naught must go to 0, plus z minus z naught whole square by factorial to q double prime z naught and so on. So, and also we have assumed that a p of z, p z naught is not 0, where p of z naught is not 0. Okay. Otherwise, it will go the identity function, 0 function. Okay. So, residue of f z at z equal to z naught, you can just divide and take the limit, multiply by this, we will get p z by q z and limit z tends to z naught, and what you get immediately, this will come out to be the p z naught over q prime z naught. So, that is another formula to compute the residue at a simple pole. But if the case second, if our z naught is a pole of order m, is a pole of order m, then the corresponding formula, I am not driving that result, the corresponding formula for the residue of the function f z when z equal to z naught is a pole of order m, then this formula will be 1 by factorial m minus 1 limit z tends to z naught, derivative m minus 1 a derivative of this term d m minus 1 over d z m of the term z minus z naught of the function z minus z naught to the power m f z this. So, limit of this, that will give the residue of the function when m is a pole. So, for just I will take one example and then come to our, say for example, if we take the function f z, which is say our 50 z over z plus 4 z minus I whole square. Suppose I take, obviously z equal to I is a pole, simple pole of order 2, of order 2. Okay, this is of second order. So, what is the residue of this function f z at z is equal to I? M is 2. So, it is 1 over factorial m minus 1 becomes 1. Here m is 2. So, derivative d by dz of this. So, simply it is the limit z tends to I d by dz, and then z minus z naught is I. So, it is I z minus I, m is 2, f of z is 50 z over z plus 4 z minus I whole square, and then take the. So, first you this will cancel and then differentiate it. After differentiating and substituting the value, you will get the answer is z. So, that way we can find. Okay. So, if the function is given and it is asked to find the residue, it is easy to either apply this one or this one. Hence, if a integral of the f z is required along the path C, along a closed curve C, which encloses the point z naught as a singular point, then one can easily find out the value of this as 2 pi I into b 1, as we have discussed earlier. However, if this curve C encloses more than one points, where the function is not defined or function has a singularity at more than one point, then in that case this formula will not help much. It means everywhere first we have to identify the region where the function is analytic, apply the Cauchy theorem to find out the integrals, and then only we can get the something about the value of this integral. So, the case is given by the residue theorem, and this result is given by residue theorem. This is known as the residue theorem. What this residue theorem says, let f be analytic, f z be analytic inside a simple closed path C and on C, except except for finitely many singular points, z 1, z 2, z k inside C, then the integral of the function f z taking counterclockwise direction around C, around C, counterclockwise along C equals 2 pi I times the sum of the residue of f z at these points z 1, z 2, z k. That is, the meaning is this, that integral of the function f z along the path C, where C is a closed curve, where the function is analytic everywhere except possibly these k points, which has a singular point. Then the value of this integral will be 2 pi I times sum of the residue sigma j equal to 1 to k residue of the function f z at z equal to z j. The proof is very simple. What we do is, we replace this remove this z 1 z 2 z n by means enclose the z 1 z 2 z n by a circle, and let the direction of this be suppose clockwise. Okay. Then if I go along the path C, then what happens, that when you move along this curve along this direction and then come back again this direction like this. So, what we get it, we are getting a region, where the function is analytic. So, integral of this curve C outer boundary plus this integral must be 0, but here the integration is taken in the clockwise, here it is in the anti-clockwise. So, we get from here is that integral of the function f z along the outer boundary will be the sum of the integral of the function f z d z along the inner boundary, say C 1, C 2, C k. This is the sum k equal to 1 to j equal to 1 to m k. Now, this each integral is taken along a curve which contains only one singular point. Hence, by the previous result, the integral of the function f z along a curve C, which encloses only single point, is 2 pi I times the residue of the function at this point. So, this is equal to sigma j equal to 1 to k and 1 to k residue of the function f z at z is equal to z j and 2 pi I. So, this proves the results. Okay. So, just one example I will just give and then finish it. Suppose I take this integral 4 minus 3 z over z square minus z d z. Suppose this integral along the path C, where C is such which encloses the point 0, 0, 1 and so. If we look the function f z 4 minus 3 z over z, z minus 1, it has a singularity z 0 and 1. These are the two singular point at this, z equal to 0 and z equal to 1, both are the simple pole only. Suppose the C encloses both the point 0 and 1, then the value of this integral will be 2 pi I times the sum of the residue at z equal to 0 plus residue at z equal to 1. If it encloses only one point and one is outside, then the value will be equal to 2 pi I times residue at z is 0, 1 is here, and third case, suppose it both the point 0 and 1 is outside, then integral along this curve will be 0, because the function becomes analytic. So, only thing is you have to compute the residue at 0 and 1, and residue at 0 means multiply this by z and take the limit z tends to 0, you can find the residue at 0. when z is 1, multiply by z minus 1, take the limit at z tends to 1, you get the residue of the, hence we get there. So, what we conclude that the integral, when you find the integral of the function along a closed path, we have to see that the function f z, what are the singular point of the function and whether they lie, where they lie. If they lie inside, then accordingly the formula will be there. If lies outside, accordingly the value will come, or one lies inside, one lies outside, then also according. Means in all the cases we are able to apply the residue theorem to get the value of the integral. Thank you very much. Thanks.